Hi, my name's Paul Rayson from the School of Computing and Communications at Lancaster University and Director of the UCROL Research Centre. In this video, I'll talk to you about the semantic annotation of text using computational linguistics methods. So first of all, we need to take a little bit of our diversion into corpus annotation and show you where semantic annotation fits into this hierarchy. So here you can see the hierarchy of linguistic levels of annotation going from pragmatic discourse through semantic, syntactic, lexical, down to morphological, phonetic, and phonological. So as you go higher up this hierarchy, the more difficult it is to do this corpus annotation process completely automatically by computer, and that makes it more difficult to do and less accurate therefore. So some of these levels still only get applied manually by people actually inserting annotation or tags into corpora themselves. Semantic annotation that I'll talk to you about here is possible to do at a certain level of accuracy completely automatically. So just to give you some examples of these, the most well-known level of corpus annotation is grammatical or part of speech tagging. And this is where you use the computer software to insert a part of speech label or a word class label for major parts of speech, noun, verb, adjective, adverb, etc., but also subclasses within those. So the corpus annotation result would look like this at the bottom of the screen here, where for each word in the text you assign a label, here shown in blue, which indicates the part of speech of the word it's attached to. And this can be done automatically with a high degree of accuracy for many modern languages. Another level that we've worked on here at Lancaster is partial or skeleton parsing, and here you'll see that the annotation is applied not just at the word level but at the clause or the phrase level, here indicating things like noun phrase or verb phrase. Now, at the semantic annotation level, we do the same kind of thing. We apply a tag or a label to each word in the text, and I'll tell you more about the detail of this in a moment. But here, just to give you an example, you can see we've assigned these semantic labels to each word in this text. So these indicate things like E3, emotional states, M6, location and direction, and G3 is warfare, for example. So I need to help you understand a little bit more about our version of semantic annotation by distinguishing it from other types of semantic annotation that you might have heard of or can search for. So in computational linguistics or natural language processing, one of the well-known versions of semantic annotation is called word sense disambiguation. And here what the task is trying to do is to allocate a label or a tag or some distinguishing feature to each word in the text against an off-the-shelf dictionary. So here you might be trying to determine which of the many senses of the word set is appropriate in the context. Our version of semantic annotation is more coarse-grained than this, and I'll show you some examples in a minute. Other types of semantic annotation are things like semantic role labeling using FrameNet or named entity recognition, where you try and automatically extract all names, places, dates, times, organizations automatically from a text. Sentiment analysis could be used in mining opinions on certain products or political parties, perhaps, and seeing whether you have a positive or a negative view on a certain topic. And often this gets applied to online social media. Another version of semantic annotation is content analysis, and this gets used in psycholinguistic applications for automatically assigning content or extracting content-related information from a text. So, more detail now on our version of semantic analysis, and we built a system called USAS, the Ugrol Semantic Analysis System. So what does it do, and what were we aiming to do with this system? Well, we wanted to assign tags or annotation to every word in the running text, not just selected words. So some of the applications in the particularly content analysis area, such as Diction or Luke, LIWC, or Regressive Image Dictionary, just take part of the set of words in the vocabulary and allocate meanings or senses, or try and pick out content in certain areas. What we wanted to do was to semantically annotate every word in the text. And as I've already said, the sense that we're trying to distinguish here is a coarse-grained sense. So it's not the fine-grained level of detail that you might find in a printed dictionary, but enough to determine the semantic field or the meaning of a word. We didn't just want to make a system that was task-specific, for example, looking at the analysis of market research interview transcripts, but to be more general purpose than that, so we could pick out a general meaning of the text. We wanted to have a flexible category set with a hierarchical structure so that one could conflate certain levels of the hierarchy if you wished to become even more coarse-grained or more fine-grained, depending on the analysis that you were undertaking. One of the particular features of our system is that we annotate not just single words, but also multi-word expressions. And there's lots of different types of these things, including in the list here, phrasal verbs, noun phrases, proper names, and true idiomatic expressions. So, for example, you wouldn't want to separately count or annotate the two-word phrase New York. You'd want to count that as one item together so that you could extract the meaning of that. There would be no point analysing the separate words in Living the Life of Riley, because it means one thing as a whole. So the way we do that is to call them multi-word expressions. We annotate those as one block. Phrasal verbs could actually be discontinuous. They don't have to be consecutive words. So we also annotate those as one item. So the approach that we took was to use semantic fields. Sometimes we'll call these semantic concepts or semantic domains, but the overall definition of this is that they group together word senses that are related by virtue of them being connected at some level of generality with the same mental concept. So this includes various lexical relationships, not only synonyms and antonyms, but hyponyms and hyponyms. So, for example, we would have a semantic field or category called education, including, for example, these words and others: academic, coaching, coursework, deputy head, exams, PhD, play school, and so on. So you can see that there's various parts of speech here, but we're assigning all of these words and multi-word units into this semantic field of education. So overall, this is the way that we divide up the world. Here's our top 21 major domains in the semantic hierarchy, and this was originally based on Tom MacArthur's Longman lexicon, but we subdivided a few of the top level categories and expanded the hierarchy lower down. So this is the way we divide up the world. These 21 major semantic categories, picking out education before, but also government and public. So every word or every phrase in the text we want to assign into one of these 21 major categories, and underneath this top level we also have 232 subcategories, and I'll show you some examples here. So how does the system work? Well, we need to give it lots of information, lots of knowledge to draw from. So we give the system a very large dictionary that has information as presented here. So one of the entries in our dictionary could be the singular common noun presentation, and in the dictionary we would say here's 4 possible semantic tags that this item might have in text. So Q2.2, for example, is speech act, or K4 is theatre and drama. So the job of the semantic tagger is to take this underlying semantic lexicon that we've given it and choose which of these 4 possible semantic tags is correct in a given context. So it's going to look to the surrounding sentence and say which of these is most likely in that context. And I'll tell you more about the methods that we use for that in a moment. As well as the single word dictionary, we also have this multi-word dictionary that I've mentioned of around 19,000 items. So some of these are quite tightly specified, as in this example, travel card, where we would give it this tag M3/Q1.2. M3 is vehicles and transport, Q1.2 is paper documents. So that together with that slash represents that one sentence. So you can see there an example of something that we call a slash tag that sits across 2 parts of our semantic hierarchy. Some of the entries in the multi-word list are much less well defined, so we would have a list of all of the templates to do with names of people or places. So we wouldn't need to list every single name of every single road in the world. We just use a wildcard pattern to specify that. We also have that similarly in the single word lexicon, so everything ending in kilograms can be assigned a measurement weight tag N.3. If the system doesn't know a particular word in the running text, then we use WordNet to look that up. First of all, we use the WordNet synonym sets to say what are the synonyms of this unknown word. We would then look up those synonyms in our dictionary and try and assign a category based on that. So that's the knowledge that we give it, that we've built these resources by hand, and we give the semantic tagger these bits of data. Then, as I say, the job of the semantic tagger is to work out which of those possible tags is correct in a given context. So we have 6 different methods that we use in the semantic tagger. The first of these is here. So we use the part of speech tag. So first of all, before the semantic tagger runs, we run the text through a very accurate part of speech tagger, in our case called clause. And this helps you determine some of the semantic tags. In this example here, I've got the word spring. So if you know very accurately that this word spring in this context is a verb, then you can actually throw away these 2 sentences to do with the season or the metal coil, because you know that the verb just has this jump semantic tag. So that helps us quite a large amount with the semantic disambiguation. Second of all, here the method is a general likelihood ranking for the tags in the underlying dictionary. So in that example I showed you before with presentation, the semantic tags are listed in likelihood order. So we've used our intuition corpus knowledge that we have available to us to determine this likelihood ranking. Another example of this would be green, referring to colour, is more generally frequent in general language, in the general corpus, if there is such a thing, than green meaning inexperience. So we would list that colour sense, that colour semantic field first before the inexperience sense. And generally what the system does, unless it has any further information, it would prefer the first tag in the list if there's no other knowledge coming into play at that point. The third method of disambiguation is overlapping multi-word expression resolution. So it might be the case with some of these semantic templates, some of these semantic multi-word expression rules that we have, that they're very loosely defined. If we use a wildcard, for example, you might have the situation where you've got two or more templates applying at a certain point in a sentence. So generally we have a small set of rules which say if the idiom, if the multi-word expression is shorter or more well specified, then prefer that possible sense than something that is less well specified or longer span. The fourth method and the fifth method of disambiguation pretty much used together. So if you know in advance that your text that you're going to load into the system is to do with politics, then you can pretty much guarantee that any occurrences of the word party would be to do with that meaning rather than an entertainment event. Also, if you know that you can identify very reliably at a particular point in a text the sense of a word, then pretty much you can guarantee that in the rest of that text, if it's about the same topic, the other occurrences of that word would have the same meaning. So that's the 1 sense per text, 1 sense per discourse hypothesis. Finally, we have a set of template rules which are similar to the multi-word expressions, but where we don't want to define one phrase being tagged as one semantic category. These are template rules that are looking at the surrounding context, and for very frequent errors in the system, we can say, in this context, the semantic tag on the particular word is this. So one of the examples we use here is the auxiliary verbs. Our underlying part speech tagger doesn't distinguish auxiliary from main verb usage of be, do, and have. So we defined some short template rules using word and part of speech sequences to distinguish auxiliary from main verb use. The other example that I've got here is the verb account. If you have, or the word account, if you have some context related to bank account or other similar contexts like that, then you know that this is the financial sense rather than the narrative account. So you can distinguish using the surrounding context there. So how accurate is the system that we have built? Well, we tested this on around 125,000 word corpus and corrected, and when you check which are the correct tags in each context, we have an error rate of 8.95%. Starting off with the full list of semantic tags applied by our underlying dictionaries, you would end up with about half of the words in running text being ambiguous. So that's this ambiguity ratio, 47.7%. With the 6 methods that I've just explained here on the previous slides, you can reduce that level of ambiguity down to 17%. So using our set of rules, set of disambiguation methods, not all of this ambiguity is resolved. But as a final step, as I mentioned, the system chooses the first tag in the list, and doing that gives us our error rate of 8.95%. So we claim accuracy on general text of our system of 91%. And that's good enough for most applications, but obviously we're constantly working on extending the underlying dictionaries and adding new methods to the system. So that's the system as it stands. I want to just finish off here with some recent and ongoing research where we've used the semantic tagger and extended it. So, as I say, the semantic tagger is built on a modern way of dividing up the world. But imagine you just stepped out of your time machine using your laptop, carrying your laptop with you, and you wanted to analyse this text over here on the right hand side from 1696. What would be the possible problems that you might have applying a system like this to this text? Well, probably more likely you're a historian sitting at your desktop computer, maybe accessing this historical text using one of the many online interfaces. Still, you face the same problem. So the two main issues, as you might expect, are spelling variation and also the fact that meaning, of course, changes over time. And also our semantic taxonomy that we've used here, as I showed you, is very much a modern and Western view of dividing up the world. So two things that we're working on in the Samuels project, more details here at this website, are these spelling variation and this change in meaning over time. So as you can see here with this short extract from the version of the Bible, 1611, all these highlighted terms are non-modern spellings. So if I tried to semantically tag this particular text with the existing system, all of these highlighted terms would fail to get tagged or would be incorrectly tagged. So what we have to do is insert a modern equivalent alongside these historical variants, and we've built a system called VARD, the variant detector, to do this. Alistair Barron built the system and tested the accuracy on a wide variety of historical texts. So the idea there would be you link each of these historical forms to a modern equivalent, and then the semantic tagger would then pick up that modern equivalent and hopefully get a better result. The other thing that we're doing to address the issue of the applicability and accuracy of our modern semantic taxonomy is using the historical thesaurus of English, and I've shown you a small section of the semantic hierarchy there. So whereas our existing USAS system has 232 tags within it, the historical thesaurus has over 200,000 entries or tags or labels within it. And these are linked to the Oxford English Dictionary using dates as well. So this is very useful to us when we're applying our system to historical text. We can use historically valid taxonomy using the Glasgow Historical Thesaurus. Secondly, the other thing that we're working on at the moment is non-English versions of the system. So the version of the system I presented so far has obviously been for English, and that's mainly because of the underlying dictionary. So we're now working on new versions of this for other languages, and at the moment we have online versions for Dutch, Chinese, Italian, and Spanish and Portuguese, working on Czech and Malay as well. So the key resource that you need to extend such a semantic annotation system to another language is the underlying dictionaries. So we're attempting to build these using a bootstrapping approach to create these new dictionaries in one of two ways. So we can take the existing English dictionary and translate it, if you like, using a bilingual lexicon or a bilingual dictionary to derive a first version of a dictionary in one of these other languages. The second approach that we're trialing is to use parallel corpora. And if you have parallel corpora aligned at the word level, then it's possible to semantically tag the English section of that parallel corpus, transfer the semantic categories across using the word alignment, and then derive a new lexicon in the other language from that parallel corpus. So you can try out our current versions of these taggers on this website here. If you'd like further information about the USAS semantic tagger, please visit that website. Again, listed here, ucrl.lancs.ac.uk/USAS, where there's lists of the funding and funders that we've had for this work, and lists of acknowledgements to colleagues who have been involved in creating this semantic analysis system with me. There's also browsable versions of the semantic tag set and downloadable versions of academic papers describing the work and using the work. Also, you feel free to contact me on this email address or on this Twitter handle here at the bottom of the screen.